Right, now we're going to take a little bit closer of a look into kinetics and rate laws. So we're going to look today at the integrated rate laws. Those of you who are in calculus are going to take calculus. You're going to hear the term integral. So what these are is they are integrals of the rate law equations. Now, we're not going to look at the calculus part of it. We're just going to look at the equations that were derived using calculus. Those of you who go on to take AP Calc or in it right now, you've probably seen these equations or are going to use these equations too. And what the integrated rate laws let us do is look at the time of a reaction. So if we take two reactants at a certain concentration, mix them together, we want to know how long is it going to take this reaction to complete. That's where the integrated rate law comes in. So the trick with this is you can't just use the rate of a reaction, the instantaneous rate of a reaction, because if you remember at first they're going to go really, really fast, but then they gradually slow down, which means that the rate of change, the rate of the reaction is constantly changing. Hence the integration. What that lets us do is derive then how much time this is going to take. So for the integrated rate laws, there's a different equation for each of the different types of reactions, so first order and second order reactions. So first we'll look at first order integrated rate law. So this would be only working for a first order reaction that's an overall first order, which means we only have one reactant that has any effect on the rate, and it's going to have a single step effect. So if you double the concentration of A in this case, it will double the reaction rate. If it's mixing with something else, it would be something that's zero order, so something that does not affect the rate. So for the first order integrated rate law, this equation right here was the one that we used in the last sets of videos. Rate can be equal to either the change in concentration of A over time, or it can be equal to the rate constant times the concentration raised to the first power. So using calculus, you would integrate this rate law right here, and this would be the equation that you would come up with. And so what this does is it's the natural log of the concentration of A at a certain time minus the natural log of the concentration of A initially. So that 0 naught means initial, that T means time. And that's equal to the rate constant times time. And that's, of course, negative right there. And you see the T right there and the T right there. So this would be the concentration at this time right here. So if we let this go for 5 seconds, it would be the concentration after 5 seconds. If we let it go for 3 hours, it would be the concentration after 3 hours. And this right here would be what it starts out at, so before the reaction begins. Luckily, this equation is given to you on the AP sheet, so you don't need to memorize it. However, it is not labeled as the first order reaction rate law. You need to recognize this one right here, because you're going to see the second order here in a second. The second order looks different, and you need to be able to pick out which is which. So here is the magic of the integrated rate law, and this is kind of one of the basis of calculus really, is getting things in order to linearize, which means we make them fit into the y equals mx plus b equation. What? That equation never serves a purpose. Actually, it really does. So if we arrange this equation so that it looks like that, what we see then is with y equals mx plus b, so y, that would be our y-axis, is equal to the slope times the x-axis plus the y-intercept. And so what that means is if we plot this as the y at the concentration of time, natural log concentration of time, the k will wind up being the slope of our straight line, and we plot this with time on the bottom, and then our y-intercept would be whatever the initial concentration is. So what this means then is if we plot the natural log of the concentration at a particular time versus the time, we would get a nice straight line. This is different than what it would look like if we were to just do the concentration versus time. We saw this back in the very, very first video. Concentration versus time gives us a curved line right like that. We can't do much with a curved line, but if we get it to linearize, if we get it to a straight line like this, we can throw this down in the y equals mx plus b equation. And so our y-intercept would be the initial concentration, and the slope of this line, rise over run, is the negative of the rate constant. So we can actually find the rate constant just looking at the graph. We can also recognize this as a first order reaction because it produces a straight line with a natural log versus time graph. If we were to do this with a zero order or a second order, we would not get a nice straight line like this, which means we can identify a reaction based upon its graph again. So we can do a couple different things with this graph right here. If we've got this in front of us, first thing we can do is we can figure out what the concentration of A is after a particular amount of time. So let's say, 3 seconds have gone by and we want to know what the concentration should be. Well, if we look on this graph, right there would be where it falls, and so whatever concentration that is right there would be the natural log, and so we would have to then take 10 to the whatever the concentration of A, or whatever that value is right there, and that would then give us the concentration of A. Also, if we look at the slope of this line, so if we were to do rise over run, and we multiply that by -1, that would give us what the rate constant is, so what K is. So we can use this to find the rate constant K. We can also use this to find the concentration at any given time. We can also say, all right, we want to know how much time is going to go by before we wind up with 3 molar concentration. So we'd find 3 molar on our graph, wherever it is. We'll say it's right there. We would trace that across, and then we could figure out, okay, that's going to happen after 20 seconds. So if we wanted 3 molar, we'd pull it off after 20 seconds. So let me give you an example. Here's some data that was gotten in the lab, and we would see the time, and then we'd see the concentrations right here. Now, if we were to plot it just like this, we would wind up getting a curved line. That's exponential data. However, if we take these concentrations and natural log all of them, we would wind up with, if we would plot natural log versus time, a nice straight line like that. So natural log versus time, that means this is a first order reaction. So let's do 3 things. Let's find the rate law, let's find the rate constant, and let's find what the concentration of A is after about 50 seconds, 500 seconds. All right, first off, the rate law. Now we're not going to need to do anything fancy with this. We look at the graph. We see that the graph shows us that it's a straight line. Since it's a straight line with a natural log versus time, it must be a first order reaction. And if it's a first order reaction, that means the rate is equal to the rate constant times the concentration of A to the first. Pretty straightforward. Since we can look at the graph and tell it's first order with respect to A, we don't need to go through all the trouble of trying to figure out the exponents and the powers and all that jazz. We can just look at the graph, throw 1 down because we know what order it is. So to find K, we can measure it on the graph and do a rise over run thing. We can also use the integrated rate law to derive K. Now, since there's no units on the graph itself, I'm just going to go ahead and use the integrated rate law. So here's the integrated rate law. Since it's a first order reaction, when you use the first order integrated rate law, and we're just trying to find the K, so we use that value right there, or solve for that value. So just wave of the hand, rearrange it, and now we can go ahead and plug some values in. I'm going to go ahead and use data from time 0 and then any other time. I'll go ahead and use it 50 seconds. You could use 100 seconds or any other number that you want. Either way, you'll get the same value. So plug them in, making sure to put units on there, so molarity cancels out molarity since we're subtracting natural logs. And that gets us a final value of 3.3 times 10 to the negative third. And the units on that, since we have just seconds on the bottom, is going to be seconds inverse. And so that is our reaction rate constant, which means this value stays the same for this reaction at this temperature. So if we want to look at different data or we want to plug this in somewhere else, we can go ahead and use this since it is a constant. And finally, let's go ahead and find out what the concentration of A is after 500 seconds. So after time beyond what the graph shows has passed. So once again, we're going to use our integrated rate law. This time we're going to go ahead and solve for concentration of A at a particular time. So we're going to solve for that value right there. Alright, so wave of the hand, rearrange the equation. Now we're solving for the natural log of A at 500 seconds. We use the K value that we found in part B, multiplied by the time. Then we add that to the natural log of 0.020. So that would be at time 0 what the concentration was. And we use time 0, that way we can use 500 seconds as our time. If we were to use the concentration at 100, we'd have to use 400 seconds as our time, so it just kind of simplifies things. Now, to get the natural log away from here, because we want to solve for just A, what you use is the anti-natural log, which is the E button, lowercase e button on your calculator. And so when we use that button, that cancels out that side. We'd have to use it over there. And so what that means is it's going to be the E raised to all of that right there. And what that ends up getting us, go ahead, please type this into your calculator just so you get some practice using that E button. Make sure you get the same value that I did. And what you should get is 3.8 times 10 to the negative third. And let's take a look at units. So seconds inverse is going to cancel out seconds. We'll be left with M, which is molarity, and that makes sense because concentration, molarity. So that means after 500 seconds has gone by, we will be left with a concentration of 3.8 times 10 to the negative third molar A. So if we look at a first order reaction and we just plot concentration versus time, you see that we get this familiar curved line right there where it goes really quick at first, but then gradually slows down. And over time, that concentration is going to cut in half, then it's going to cut in half again and again. And if we were to plot that slot right there where it would cut in half, so at first it's going to divide by 2, be right there, and this amount of time has passed. And then that amount's going to divide by 2 again, and this amount of time has passed. That's going to divide by 2 and this amount. And what you notice is it's the same span of time that results in half. And keep in mind, if we start at 100 molar for this first part, the first half-life is going to get us down to 50. And then the second half-life, so this second span right here, is not going to get us down to 0. So it's not going to get rid of the other half. It just means that this value itself then cuts in half again. And so it's going to go down to 25 and then 12.5. And so the span of time from the 100 to 50 to 25 to 12.5 is always equal. And that's what we call the half-life. So it's the time it takes for half of the concentration of the reactant to decrease by half. And this is a constant value for a particular reaction, where we wind up with the exact same half-life value every single time until the reaction goes to completion. However, since rate does change with temperature, if you change the temperature of a particular reaction, you also change its half-life. So this is a constant, just like K is a constant for a particular temperature. So here's an example. We're given a graph of the natural log of a concentration of dinitrogen pentoxide over time, and we see that we get a straight line. So what type of reaction is this? Oh, it's a first order because it's a straight line with natural log versus time. We want to know what the half-life is for the following reaction. So since this is a first order reaction, we know that the half-life is a constant for a first order reaction, as well as K is a constant for a first order reaction, which means those two can be correlated, they can be related to each other. So a real quick wave of the hands, I'm going to pull this out of a hat. So the half-life of a particular reaction, the time for half of it to decay, is equal to 0.693 divided by the rate constant. And I'll show you how this is derived in class, because this is not an equation that is given to you on the AP test. You can memorize this, or you can just learn how to derive it. But in order to get the half-life, we're going to need to know the K. How can we get the K from this graph? Let's see. Oh, it's the slope of this line right here. So if we do a rise over run, we can get the slope. And what do you know? We've even picked out our values. So here's going to be our rise, and our run is going to be over to 600 seconds. And so if we do a change in y over change in x, we would get a value of negative 1.02 divided by 600. So that's going to be 1.70, negative 1.70 times 10 to the negative third. And it's going to be seconds inverse as our units, because that's what we have on the bottom. So that's our slope, but remember, to get slope into K, we need to multiply that by negative 1. So we take all this, multiply it by negative 1, which means that our K value is 1.70 times 10 to the negative third seconds inverse. And so we can take that number then, plug it into this equation right here. So 0.693 divided by our K value right there tells us that the half-life of this reaction is roughly 408 seconds. So that means as time goes on, after 408 seconds have passed, half of it is going to have decayed. And then after another 408 seconds, another half, and then another half, and another half, and another half, until eventually you run out.